Welcome to this video on reading a potential energy graph. In this video, we're going to be taking a look at how we can get a lot of information about the motion of a particle from this one simple graph that contains so much information. So the main idea here, remember, is that we're looking at the motion of a particle, and that is what's most important when we take a step back and look at the big picture. Now what I've got on this graph are a few different pieces of information. Keep in mind that this right here is just the x-axis of the graph, okay? And then I also have this purple line over here, and this purple line is actually defining what the mechanical energy of the object is at every given position. Whereas the blue line is defining what the potential energy of the function of the object is at every given position. So we can see here that the mechanical energy for the object stays the same no matter what the position is. So we're going to define here that the mechanical energy is any energy that takes the form of motion or position. So that translates to kinetic energy plus any kind of potential energy. Now, kinetic energy is proportional to the square of the velocity of the object. So we could use this equation to calculate the kinetic energy of the particle with mass m and velocity v. And u, the potential energy, is actually going to be possibly any kind of function that we'll look at. And it's not going to just be the gravitational potential energy equation that you might have learned before, but in fact it's going to be the potential energy as a function of the position, and that's just going to be defined by this function, whatever function is given on the graph. So let's just look at some significant points on this graph. Well, we've got this point right here where it touches the x-axis, and that would be a point where, of course, there is zero potential energy because it's at interacting or intersecting that point. Over here we have a point where the total mechanical energy crosses this potential energy curve. And that's something that's going to be known as a turning point. And we'll get into that in a little bit. Now what we want to do first is remember some of the definitions that we'd come up with from before. And one of them was that we could determine the force acting on the particle, and of course this is a conservative force, by taking the negative derivative of the potential energy with respect to position. We could also go the other way, but get the potential energy as a function of position by taking the negative integral of the force with respect to position. And here I'm of course just using x, and you could put r here as your generic position vector. Let's take a look at why we have this negative sign. So one thing that's super important here is that where the derivative is equal to 0, which would be right there, and we could argue that somewhere out here it's very close to 0 as well. These are going to be points that are considered to be equilibrium points. Now, what's very important to note is that an equilibrium point does not have to occur when the potential energy is 0, because I could have shifted this whole function up like this, and that would still be considered an equilibrium point. An equilibrium point is actually going to happen where the negative derivative of the potential energy is equal to 0. Or another way of saying that, an equilibrium point occurs where the derivative of the function is 0. And so you can see that would be there, and it could also be right over here. Now this is going to be called a stable equilibrium point. This is going to be called an unstable equilibrium point, possibly. And the way you could think about that is that if I displace the particle in either direction, it would come back to this point. This one's unstable because if I displace it just a little bit that way, it has a much greater chance of rolling back towards a more stable point. But they're both places where the force of the acting on the particle is actually equal to 0. Or you could say it's the place where the derivative of the function is equal to 0. So let's see why this is a negative value. Let's say that I physically have basically a little dip in the ground, like a little valley over here. And I take a marble and I release the marble. Well, gravity pulls it down here to this point, and if I displace the marble up this way and drop it, gravity will displace it down this way. So when I'm trying to determine at this point right here, what is the force that's acting on this object, what I would have to say is that the force is always going to point against where I'm pushing it in order to give it a stable equilibrium location. That means that this has to come out to be a negative value. Otherwise, it would imply that the object was not displacing back to its stable equilibrium point. Now, what's kind of interesting here is that if we know that the kinetic energy and the potential energy always add up to the mechanical energy, then that means that I could pick any point on this graph and I could know up to here the potential energy. That would be that exact value of potential energy, and then the difference up to the constant energy line would be the kinetic energy. So this is a cool way to be able to look and see what the kinetic energy would be at any point here. So I'm going to ask you a couple questions. You can pause the video and try to answer them yourself. The first is, where is the kinetic energy the greatest? Hopefully, if you paused the video, you saw that it would be this point here, because that would be the point where the potential energy is the least. Another way to look at this would be that the place where I'm at stable equilibrium actually had one of the highest kinetic energy values for this particle. Another question I have for you here is, what do you think the turning point defines for the graph, but in a physical sense? Well, hopefully you can see that's the point at which the object would literally have to turn around and go back because it does not have enough total mechanical energy to exist beyond those places on the graph. Now, an example of where this could look kind of interesting is if this blue portion here actually went up above this place again, we could say that there's another turning point right here and actually one right here, but a particle that's existing between, let's say, 3.4 and 0, or just close to 0, so maybe let's say 0.2, this particle could not get out of the positions between, say, let's make it 0.3 and 3.3. So it couldn't get out of that space because it doesn't have enough mechanical energy to get beyond those places. Now over here on the actual blue graph that I have, we can see that the particle can be in all of these different places. The way that we're going to calculate the turning point is actually by taking the mechanical energy function and setting it equal to the potential energy function, and we will solve for the intersection of those points, and so we could know that a turning point is going to happen at x equals whatever number of position and maybe one over here as well, and that would tell us where the object would physically have to turn around in order to get back. So some of the questions that you're going to do right now for practice questions are just different iterations of taking the negative derivative of the potential energy function to get a force function and vice versa, and then making some inferences on the actual information about the particle's motion.